Hello everyone, in this video we will talk about cross-validation, regression trees, and even random forest. Okay, so what is cross-validation? The idea behind cross-validation is to be able to generalize our model in such a way that it will perform really good even when we're using unseen data, with new data. So one of the common error is that typically people use the same data that was used during the training also to evaluate the model. So the problem that it creates is that you will overfit your model. That means that it's a model, when you have overfitting, is when you have a model that is really good with the data that you use to train the model, but when you expose that model to predict using new data, the performance drops. So that's what we call overfitting. So one of the uses of cross-validation is to avoid overfitting, but there are other purposes of cross-validation. The second purpose or the second goal is to compare different algorithms. For example, for regression, you can compare linear regression with regression trees, random forest, XGBoost, different algorithms. So you can compare the performance using cross-validation. And a third common use of cross-validation is for parameter tuning, hyperparameter tuning. That means that some algorithms, they have hyperparameters and you don't know the value. For example, in trees, in regression tree, you will learn in this video that you can define a hyperparameter that is called the depth. That means like the number of levels that tree is going to have. So before running your model, you don't know which value to assign to that hyperparameter. So you can use cross-validation to compare multiple max depth values. Same idea with other algorithms. Okay, so there are multiple ways to perform cross-validation. The general idea is that we're going to split our data in training set and test set. So let me show you one of the most popular cross-validation techniques. It's k-false cross-validation. So let me show you this graph. I believe it's clear if we follow the explanation here. Okay, so originally you will have 100% of the data, that's all data, right? And then we're going to split our complete data set in two parts. So we have the training data and the test data. There is no like a scientific way to define the exact percentage that you're going to use for the training and for the test data, but typical values are 80% of the observations will be in the training data, 20% will be in the test data, or you will see also 70-30, like 70% of observations go to the training data, and the remaining 30% will go to the test data. So those are the common values, 70-30, 80-20. All right, so please notice that we're going to use the training data for the validation part. The test data, you have to hide it. Do not use it because you don't want to leak information for the training part. The idea is that the test data will be used later to analyze how good the best model, how good is the best model with new data, with unseen data. Remember that the general idea is to generalize, right? So please make sure that you don't use your test data during the training. Okay, so we have only the training data. And please note that now we split that training data in k-false. That's why we call it k-false cross-validation. In this specific example, k is equal to 5. Typically, you will see k between 5 and 10. 5 is fine, it's a common value. Again, there is not like a scientific way to pick k. Typically, it's more like empirical. Yeah, most people will use 5 for sure. All right, so we have k-false, 5 false. So we split in 5 equal parts our training data randomly. One of the ideas that, or what you should expect is like typically these packages, they are gonna ensure that the observations in each fold they like follow same distributions. That means for the independent variables and even for the y variable, they should be distributed like equally in these 5 folds or in the k folds in general. All right. So now we start our training. So to make comparison, so let me show you how it works. So we'll have 5 splits because here k is equal to 5. So in the first split 1, please notice that fault 1 will be used for a validation. That means that this fault 1 is not involved in the training process. So the remaining 4 faults, fault 2, 3, 4, and 5, you combine them. It's like, imagine that you put them together in a single table, this data, right? You use those 4 faults to create the model. Imagine that our first algorithm is linear regression. So you use these 4 faults, these observations, to create a linear regression model, and then the performance metrics for that specific model will be evaluated in fault 1. Remember, fault 1 was not used here in split 1 in the training stage. It's only used for in the validation process, right? It's just to evaluate the performance of the algorithm, of the model, using unseen data. So fault 1 will be used for that. Then in the second split, similar idea, but now here fault 2 is the one that is reserved for validation. So you take fault 1, 3, 4, and 5, you combine them in a single table, you train again a new linear regression model, and you evaluate that model in fault 2. So you have the R-square of the performance metric for split 1, and now you have one more metric for split 2. So you keep going for the remaining splits, and in the split number 5, same idea, but now fault 5 is going to be used for the validation part. So we combine fault 1, 2, 3, and 4. We train a new model, and the linear regression model, and then you evaluate the performance here. So you have 5 metrics here. So you can see here like the consistency of the performance of that specific algorithm. Okay, so for linear regression, you might have like the average R-squared under different circumstances. You can have even the standard deviation, and you can do the same thing for other algorithms, not just the linear regression. You can compare it with the regression tree or random forest, and for each algorithm you will have the same process, like the 5 splits, and you will have like an average metric of performance. So instead of having just one, like that was like before cross validation, when you do this, you see, okay, how good is going to be the model in different in different validation tests, right? Okay, so once you have the performance for linear regression, regression tree, random forest, let's say that we're comparing those 3, you can pick the one with the highest performance, and that will be the winner, like the algorithm or the model you're going to use. But the question, let's say that random forest was the best algorithm here, so which one are you going to use? Like the one from split 1, split 2, split 3, split 4, split 5? Because remember that for each algorithm you will have like 5 models. So maybe you're thinking, no, I'm going to pick the one with the highest performance. Well, that's not correct. The idea here is once you pick which algorithm you're going to use here to solve this problem, then you have to go back and you're going to use now the complete training data to train the model using the winner, the algorithm that you picked from the cross-validation part. So if I said, let's say that random forest was the best, then I use the complete training data to train a random forest, and now finally is when I'm going to use the test data. I haven't used the test data at all during the process, but now I'm going to use it with the best model to see how it's going to perform. This is really important, because remember that those predictive models, what we expect is that once we deploy them in real life, in a company, in a business, the idea is that they're going to perform well, right? So you need to check that. You need to test them, and the best way to do that is with unseen data, right? With new data. So that's what we're doing here. We're using test data finally to see if the performance is similar that the one showed during the cross-validation process. So it is expected that it shouldn't change that much. Like typically, it's not going to be exactly the same, but the idea is that you shouldn't have like something like higher than 10% of the previous value. So that will be like a reference, like 10%, no more than 20% for sure. Because if there is a huge gap in the performance of the model in cross-validation and test data, then that's what we call overfitting. Somehow our model is not doing a good generalization. Okay, so let's solve a problem using trees, random forest, cross-validation. So this is a regression problem. I'm going to provide a data set. This is an old data set. It's from the 70s, like 50 years ago. So the data set, the y variable, the dependent variable, is the median value of houses in a specific area. So we wanna predict that, the median value of the houses in the area. And there's different x variables or predictive variables, such as the crime in the area. Let me see some of them. Whether the Charles River is close or not to that area, the lake contamination in the area. What else? The age of the house. There are other metrics, there are other variables. Let me see real quick here. LStat is the lower status of the population, so it measures like poverty in the area. Okay, and I'm going to explain more variables once we're using them in case they are needed. Oh, this one is important. RM is the average number of rooms. All right, so we're gonna load our packages. We have used pandas, scikit-learn. This is new for us. It's sklearn or scikit-learn. So from scikit-learn, we're gonna use the models: the decision tree regressor, random forest regressor, and also we're gonna split our data. Remember that we need that for the cross-validation, and also the cross-validation will be handled by some methods from scikit-learn. I think I already mentioned this, but I'm gonna say it again just in case I haven't. Scikit-learn, it's really a popular machine learning library in Python. So the documentation is really good. They have a lot of examples, and you can solve most of the problems, like the typical problems in machine learning. So regression problems, you have them here. The different algorithms, they have some data sets here. Classification problems, clustering. We will go over all of them, not in this video, but right now we're solving regression problems. In the upcoming weeks, we're going to work classification and some clustering. But we also have dimensionality reduction, model selection, and preprocessing. So it's a complete package. All right. So we load the data. Remember to upload the file, boston.csv. So I already have this part of the code because we have like done it several times already. So we read the data. This is the complete data set. So it has like 406 observations, 12 columns, 11 independent variables, and the response variable. So our y, it's this one, MEDV, that's the median value of the houses or in the area, and the different independent variables. So this is a pair plot to see the relationship between the variables. It will take a lot of time. I go over all of the plots here, but let me at least check the y variable, which is the median value, versus the x variables. So with crime, so it's not a clear trend, but at least you see that the maximum values decrease. The maximum value decrease as the crime rate increases, right? Which makes sense. Let me just analyze those plots where it's really clear that there is a pattern. For example, in RM, remember this is the average number of rooms. So as the average number of rooms increases, the median value increases. That makes sense, right? So this one shows a high relationship between the two variables, the y and x. Let me see what else we have here. The LStat, remember this is a metric of poverty in the area. So this one makes sense. Makes sense because as the lower status, as the poverty rate increases, then the median value of the houses decreases, right? All right. So it's important to perform an EDA where you analyze the y variable versus the x variables, but also the x variables, all of the x variables, and then just to check the correlation and relationship among them. This is really important. Okay, remember that when you create the model, it shouldn't be a surprise which variables are in the model, which variables are significant. That's why it's important to carry out our exploratory data analysis. All right, so let's prepare our data. Let's split our data. So I'm going to create an X matrix or data frame. Alright, so in the X, I'm going to use Boston. I need to drop the column of the median value because that's Y. So I'm going to drop that specific column. And in the Y variable, we will use that column that we're dropping, right? Okay, so now we have the X data frame and the Y. But remember, the idea is to split them in train and testing. So let's create X train, X test. Let's create Y train and Y test. And the first method that we're going to use is train, test, split. So what is required here is, okay, what is the X variables, the Y variables, the Y variable because it's just one, and the test size. Here I'm going to say 20% or 0.2. That means that when we're splitting the data, 20% of the original data will go to a test set and the remaining 80% will go to a training set, right? And we need, of course, all X values and observations, and same thing with Y. And at the end of this, we will get X train, X test, Y train, and Y test. So we'll get these 4 objects here. Okay, so now we have created we have organized our data. We haven't trained a model yet. So let me show you a tree, how it looks, before we perform the cross-validation analysis. But I think it's important that you understand the trees. So let me create a model real quick. So let's use a decision tree regressor. So it has different hyperparameters, max depth, max future, leaf nodes. So for now, I'm just going to use max depth. This is arbitrary. This is not you have to pick 3 all the time. This is the number of splits that it's going to perform, or the number of levels that it's going to show the tree. So this means that it's going to have like 3 levels. I'm going to show you that soon once we visualize the decision tree regressor. You have to be careful with the max depth, because if you go high, like 5, 10, it depends on the number of variables and observations, you can overfit the model. So I'm going to use 3 initially. Typically what you do is you test different values, like 3, 4, 5, 6, 7, and you check how the performance of the tree. So for that you use cross-validation or grid search. Grid search is also a technique where you compare multiple hyperparameter values. Okay, so let's keep training our model now. I'm going to create the model 1. I don't want to use this model to predict, it's just to show you how it looks, the tree. Okay, so I'm going to train the model. I'm going to give them the X values from X train and the Y values from Y train. So with these 2 lines, you will be able to create the tree. So it will exist, it's already trained. And now, I'm gonna the following lines, it's to be able to visualize that tree. So let's do that. Let's visualize our tree. This is just the size. And now with this we create a tree. Triple tree, model 1. The filter names is just to display the names of the variables. They are here in X, remember in X. It's a data frame with only the X variables. So I'm going to use the columns from that data frame. So it's training the model now, then I'm running, it's training the model, and then it's gonna show the tree. Oh, I haven't, oh no, I did. Okay. So first thing about trees is like, for the tree, the most important variables will be always at the top. The most important variables will be always at the top. That means that in this case, Rm, the average number of rooms, it's an important variable to predict the median value of the houses. That's the first interpretation that you will take from the tree, right? There are some variables that won't appear in the tree. They won't make it because they are not that important, at least for the tree. Okay, so let me show you how it works. So initially the tree, when scikit-learn is creating the tree, it's gonna try to use it's gonna compare like different variables here on the top of the tree, and it's gonna compare also different splits. So for example, for Rm, it found that the best way to minimize the error here is when you have a split of 6.9. What is the meaning of this? The question here is, okay, if the average number of rooms is less equal than 6.9, so you go to the left if it's true, right? If not, if the number of rooms of the observation is greater than 6.9, 7 or more, then you go to the right if it's false. Now let me show you the meaning of all of this information in each of the nodes. So the first part of the node is just the variable and the value that you're going to use to compare whether you should go left or right. Then you have the metric of performance. This is the error. This is an error. How do you get that error? It's just a comparison between the real values. In this case, samples, we have 404 observations here. Maybe you're thinking, oh, why we have less than, because originally, if you remember, we had 506, right? But remember that we split our data. We have training and test set. So that's why now we have 404, because this is just the training set. Okay, so for the 404 observations, the average value of the dependent variable, the median price of the houses, it's 22.5. This is in thousands of dollars. Remember, it's that low because this data set is old. It's like from the 70s. So how do you get the error here? It's just a comparison between the real value of this observation, so the 404 observations. Remember, you have y that's given in your table. You know the median value of the houses, and then you compare it with this mean value with the 22.5. That's how you find the difference, square the sum of that, and this is like an average of those errors, the square errors, or the sum of that. All right, so let's see if this makes sense. So again, if the number of rooms is less than 6.9, we go to the left. Otherwise, if it's greater than that, we go to the right. So let's see, let's compare the nodes from below. I think this makes sense. Please notice that the houses that are with the number of rooms below 6.9, the mean value is 19.9, while those houses that with an RM greater than 6.9, the median value is 37.3. It's way higher, right? Almost twice. So that's why that variable was selected, because it's good to filter our data and to separate our observations. Okay, so now the variable that is using in the left part, it's the LStat, the lower status. Please notice that this is not a coincidence. When we were checking our plots initially, even though we didn't spend a lot of time, we noticed that the variable with a higher relationship with the median value, or the y, or dependent variable, were the Rm. Remember, there is a strong correlation here, a strong correlation, and same thing with LStat. It has a strong correlation. So that's why now we see Rm and LStat on top of the tree, right? So it's not a coincidence. It's not a coincidence. That's not a coincidence. Okay, so it continues now with LStat. Now we have here 344 observations. Then if the LStat is less than 14.3, you go to the left. If it's greater than that, you go to the right. So please note that if the poverty in the area is below 14.3, so the median value is 23.4, But if it's the poverty level is greater than 14.3, the median value is 15, so it decreases, right? Which makes sense. If there is a higher poverty level, so it is expected that the value of those houses is going to be lower. So it makes sense what we're finding here. So the tree continues splitting, this in the using these values for the different variables that were found as relevant or significant. And now at the bottom of the tree we have the leaves, and this is where we get our predictions. Please notice that the max depth, the depth that we use when we're creating the tree, was equal to 3, because we have one split here, one or first level, then a second level, and then a third level, right? So 1, 2, 3. So if you increase the max depth, maybe you will get more levels. Again, that's not good or wrong. It depends on the problem, number of variables, number of observations. So you need to check, you need to test different values for the max depth. Okay, so here is where you make the predictions, in the leaves of the tree. So let me show you the interpretation. For example, for this one, we have 199 observations here, right? So if you have an observation that it's located here, then the y-hat of your prediction is going to be 22.843. So how do you get to this part of the tree? Let's go over. So let's go over how to use the tree. So imagine that we have an observation where the Rm it's less equal than 6.9, so we move to the left, right? Then the L stat, let's say that is below 14.3, so for that specific observation. Then you check another variable, which is this. This is related to distances. So if it's greater than 1.3, that's a metric for that variable, then you will be located here. So for that observation, the y-hat or the prediction is going to be 22.843. So that's how you use the tree to make predictions. You just follow the conditions here. You evaluate the conditions, and you will get, to one of the leaves here on bottom of the tree. And the value that you see is just the average value of the observations in the training set, and that will be the prediction for a new observation. Now, something important that I want to mention here is that it's an advice. The tree, in my opinion, is not good for prediction. I mean, for prediction, yeah, you can use it, of course, but it's not only for prediction purposes. I highly recommend you to use trees also in your EDA. During your exploratory data analysis, they are really, really helpful to understand data, because now you can understand which variables are relevant, and not just the variable, also at which levels or which specific values of the variable they are relevant to split your data and understand all the variability that you have in your data set. So this is again a great tool, not just for predictions. It's really important also to understand your data. Okay, so this is about the trees. I'm gonna upload one more video about the trees to show you like some examples. But now I'm gonna use cross-validation for tree models and random forest models. All right. In this problem, let's say that we want to compare two algorithms, regression tree and random forest, and just pick the one with the highest performance. So let's do our cross-validation. So for the regression tree, I can use the same thing that I used before the plot, but just for your code, and I prefer to add it here again. All right, now I'm going to use the cross-validation. It's cross-val score. This is going to perform a k-fold cross-validation. It's going to take, it requires the model, right, this one. It requires the data, x-train and y-train. Remember that the test data is not used during the cross-validation. We reserve that data just to test the algorithm in, under new conditions. This is the k value, 5. So we want to split our training set in 5 equal parts. It takes time. But typically the decision tree regression shouldn't take that long. For the random forest, yeah, that one takes longer. Okay, it's taking way long. Okay, finally. So now what we're getting here, if you notice, we're getting this is a metric for the first split. For the second split, this is like the R square. This is the R square. Even if for one it wasn't that good, right? So now you can see like the consistency of the tree for the different splits. Now, my advice here is to you should save this information, the scores, and it's better just to see the mean value of the standard deviation. Compare it with the random forest. Okay, so while it runs, let me start writing the code for the random forest. So for random forest, okay, I have the result. So this is the mean value for the R square. It's 0.61, it's low, and the standard deviation was equal to 0.2. So now once we create the random forest, we will compare the mean values, right? Because that's the performance of the R square, but also we'll see the variability. Standard deviation is a metric of variability. So we want to reduce also, we want to increase, we want a high mean value, but we want low variability, right? Because this is not good to have this uncertainty. It's also like a measure of consistency. Okay, so let's do our random forest. Let's create our model. So you can guess how random forests work. So random forest regression, what it happens is it's going to create multiple regression trees, right? And it's going to use all those regression trees to make the prediction. So pretty much each tree is going to make a prediction, and then you just take the mean value of those trees, and that will be the prediction of the random forest. There are different versions in how to create the trees. Alright, so for the random forest, we can also add the hyperparameter of max depth. You also have the n estimators. This is the number of trees. You can increase that value. Like you can use 500 trees, 1,000 trees. It's gonna take longer, but yeah, I mean we have the computational power nowadays to do that. And typically, random forest is going to be better than this tree. Okay, so now let's do the scores. Cross-valid score. This is the random forest. This is the cross-validation. So we add the random forest, right? This is how we call it. We provide the data, X train, Y train, CV equal to 5. And then we want to take the mean value and the standard deviation. This one is going to take longer. Oh, it's not. I have an error because I didn't provide a value for the max depth. I did not provide the value. Okay, so now we get the result. Please notice that the R square is higher. The previous one was 0.61, this one is 0.77. So the performance is better. So this suggests that if you just have these two options, you should use random forest. That's the suggestion, and not just the mean value is better. Also, please notice that the standard deviation is lower, so you have less variability. So this one is more consistent in the performance. So now that we have picked random forest, we need to create the model, the model that we're going to use from now on. So how do we do that? Remember what I told you. Once you compare the algorithms and you pick one, now you go back to the training data, the complete training data, and you create the model, right? And then this is when you're going to use the test data to see how good is performing that model. Okay, so let's train the best algorithm with the complete training set. So for that, we have the random forest regressor. We use max depth equal to 3. Even this is an opportunity for improvement. Even though we know that in the current version the random forest regressor is working and it's better than the tree, but we haven't we haven't tested different values for the max depth, so we can do that. Same thing with the number of trees. We can change the number of trees to see if it improves the performance. All right. So now I'm not gonna do the cross-value score because we already we completed the cross-validation part. Now we need to train the model. So let's create a model. We'll feed the model the complete training data. And now that model exists here. Now what is important is we need to check the performance of our model. We need to see how good is that model, how good is that random forest with the training data, and compare also with the test data, because we haven't used the test data. So let's check that. So we're gonna see the performance in training. This is just for reference. So it's the name of the model, dot score, X train, Y train. So the performance of the model using the complete training data. But now let's add the same metric but using the tested data. And this is really important because again, we want these two metrics to be close to each other. Performance is test. So now we're going to use for the first time, since we start the problem, X test and Y test. We haven't used it. So they are really close to each other. So it's 0.86 to 0.865. That's good. That's good. In general, this is what we want. We want to keep the same performance. It's normal that sometimes it drops a little bit, sometimes even it goes higher. But the idea in general is that it should be like, close. No, I mean, it shouldn't be like the distance between the performance in training and test shouldn't be more than 10%. That's like for sure no more than 20%. That will be depend on the application. But if you see, for example, in training 0.86, but then in test 0.5, that's bad. That's bad because your model is not doing a good generalization. It's overfitting, right? Because it's really good with training, but not good with test. In this specific example, it's working. Now, what will happen if you rerun this code, if you follow these steps, most likely you will get a different number here. That's normal because when we're doing the splits, for the training test, this is performed randomly. So your training set is going to be different than mine and different than the other students. So that's okay. That's okay. That's normal. But in general, what I expect is like at least 90% of the students will have the same idea. Like first, you will pick a random forest. Second, in general, they will be close. These two metrics. Okay, I'm gonna before I stop the video, I want to show you how to use the model. So winner, which is the model 2. You can use it to predict using new data. And this is the y hat. Now I'm using X test because yeah, that's new data, but this can be also a new data frame, you know, with the same variables, with the same X variables. So you can feed the model with that new data frame with the X variables. Again, they have to be coded exactly the same, and you will get the y hat. This is how you use the model. Also, this model can be exported. You can save it as an object. You can deploy it. You know, deploy this model in Amazon Web Services, Azure, or any other platform if you need that. Okay, so now I'm gonna stop the recording. I'll see you in our next video.